So very welcome everyone for the next session of our Fractal Geometry Seminar, and our speaker will be István Kolossváry from Rényi Institute, and he will talk about orthogonal projections of self-affine sets on two lines.
Yeah, thank you very much. Nice to be back here. So yeah, this is a recent joint work with Balázs and Antti. And so some of you have actually been in Warsaw for the past few weeks. So you've actually heard Antti basically talk about this. So it will be a bit of a refresher for you guys, but of course not everybody was there. So it will be new to some of you at least. And I should also mention that the slides of Antti's talks are actually online, and I think also his recording will be at some point. So if you want, then go listen to that, because it's probably worth it. So let's get into the things. And well, as the title says, we are going to be interested in orthogonal projections of subsets of RD. So we have a subset X of RD, and we're going to project it onto a line. So, and this map, we're just going to denote by projection Vx. Sorry, so this should probably be something else. This should probably be RD. Like that. Okay. And well, what's an immediate thing that we know about this? So what we're going to be interested in is what is the size of the projection in terms of its Hausdorff dimension. Okay, so this is what we are going to be interested in today. And well, there's a very easy upper bound that we can always give. What are the two numbers that is always going to be an upper bound? Well, there's one very trivial one. It's simply because the projection lives on a one-dimensional subspace, so its dimension cannot be more than one. And because the projection is a Lipschitz map, and Hausdorff dimension cannot grow under it, so this dimension cannot be larger than the Hausdorff dimension of the original set. Okay, so this upper bound we always have. And this is true for every V in our projective space. Okay, for any line. So the question is, if we introduce the exceptional directions, so let's denote it by like this. So these are going to be those lines for which this inequality holds in a strict way. Okay, so this Hausdorff dimension of the projection is strictly smaller than this minimum. Okay, and of course this set can be non-empty. Just as a very trivial example, if you want to see, if you have a set which lives as a subset of a line, let's say, but you're thinking about it in R2, well, then you can take the direction which is orthogonal to it, and if you are going to project it down this way, in this direction, the projection is going to be just a single point here. So its Hausdorff dimension is 0, but it's clearly smaller than these numbers. Okay, so that's a very trivial to show that this set can be non-empty. But actually, there's a remarkable theorem of, so now I do this and do this, right? Yes. Okay, good. So there's a very famous theorem of Marström from 54, generalized by Mantilla. 1975, stating that in some sense, in some generic sense, these exceptional directions are rare. Okay? What they say, I'm not stating it in the full generality, okay? So we are just thinking about projections on two lines today. I just want to say that before. But in any case, in the way that we want to be looking at it today, it says that for any Borel set of the d-dimensional space, so X is a subset of RT, then for, okay, so there's a natural measure that you can put on the space of lines. So according to that measure, for almost every V in, so for almost every direction, you are actually going to have an equality in our main thing. So the Hausdorff dimension of the projection is equal to this minimum. Okay. There's also a second part to the theorem, which is not important for us today, is that if your set to begin with has Hausdorff dimension bigger than 1, then it actually has a positive, then the projection actually has a positive Lebesgue measure. Okay, so there the statement's even stronger. Okay, but this is really the only part of it that we are interested in today. And as I mentioned, there are lots and lots of generalizations of this. So first of all, this holds not for projection just onto lines, but onto k-dimensional subspaces. You can think about, instead of Hausdorff dimension, how does other different notions of dimension behave under projections? You can ask a lot of different types of things as well. But that, again, I'm not going to be talking about that today. There are nice surveys on this, so you can look at the literature if you want. And so, yeah, this has been a really, really influential paper, enough just to say that the paper itself had a birthday conference. So I think that says something. So yeah, there are also measure versions of this. So we're looking about sets, but we're also going to look a bit about measures today. So there's a measure version of this as well, coming later. And so basically the main question basically motivating much of, so a large strand of research has been, okay, so we know that for almost every lines this holds. What can we say about the exceptional sets? Okay, so what can be said? About the direction of the exceptions. So this guy. So in general, actually, not much can be said. Okay, so there are some general results about saying how large can this set of exceptions be in terms of the Hausdorff dimension, let's say the original set. And actually, it's also been shown with examples that these sort of upper bounds that people have proven for the Hausdorff dimension of the exceptional directions, it can be as large as it can be with regard to these upper bounds. So in general, you can. So another type of direction that we can start to go into, and this is what we're going to do today, is to look at a specific family of sets that we are interested in. And let's see whether we can say something more specific in that regard. So remembering this as our motivating question, nope, let's do yes, this. So the other word that you saw in the title hints at what we're going to be working with today. We are going to be working with self-affine sets and measures. Okay, so those are going to be the special sets that we work with, self-affine sets and measures. Okay. So I'm sure this topic is pretty familiar to most of you. So I am not going to take too much time doing with these, basically just writing up notations so that we're on the same page. Okay, so self-affine sets. What are the ingredients? Well, we need an iterated function system, an IFS. It's going to be capital Phi for me with maps Phi1 up to Phi n. Okay, so by affine map, what we mean is that there's a multiplication with a matrix plus a translation with a vector Ti. So these matrices are invertible, D by D matrices, and they are strict contractions. Okay, and the translation can be anything. So under these conditions, we know that we have an attractor, which I'll be noting with X today, which is the union of its images under the maps in the IFS. What else do I need? So sometimes I'm going to denote the index set with I, curly I. So we can make finite words out of these, which are going to be noted by I star. We can make infinite words out of these. Those will be denoted by I to the n. Okay, and for an element of these, I'm usually going to write I with a bar on top of it. Okay, what else do I need? So this guy here, the infinite words, this is our symbolic space. Right. On the symbolic space, we have a left shift. So let me write it here. And we have our usual natural projection from the symbolic space to the attractor itself. So we can encode each point of the attractor with an infinite sequence. Sometimes more sequences can go to the same point if there are overlaps in our system. But so the image of Pi is simply the limit as n tends to infinity of taking the first n compositions along that word I and seeing where it takes your point. So this shorthand notation that you see here, this is just the of the maps, as is so common, like this. Right. Okay, so these are the notations that we need for our self-affine set. So yes, I always forget this. Which one was good? So we have our sets, and we like to put measures on our sets. So we also are going to have self-affine measures. So given a probability vector P, let's assume also that it's strictly positive. So because that's really the only case which we are interested in. Pi is bigger than 0, and the sum of the Pi's is 1. Like that. So given that, there's a unique Borel probability measure mu, which you can write as a weighted average of its push forwards. So I goes from 1 to n. The weights are exactly these weights Pi's, and we take the push forward of the measure according to the functions in our IFS. an equivalent way of saying what this is if you take this probability measure P, you take the Bernoulli measure by taking the product measure on your symbolic space. So upstairs, and right, we have a nice map which takes us from the symbolic space to the attractor. So if you push this forward with the map pi, then this is actually the same thing. Okay, so this is the other way of thinking about it. Okay, so we have our two objects. So we have our self-affine sets, and we have our self-affine measures. Okay, and so again, the question will be is, what is a set of exceptional directions when we are projecting these kinds of sets and measures? So just to record one more thing about these objects, which will come up. Oh, I have to go to a new page now, right? That's what's happening. That's what's happening. Yes. Yes, okay, so that's what happened. Okay. So these are classical results, more or less, but anyway, they're important, is that if X is a self-affine set, then there's always an upper bound that we can give for its upper Minkowski dimension or Box dimension. So this was shown by Falconer that this is, so the symbolic kind of upper bound, this is like the analog of the similarity dimension that we're familiar with for self-similar sets, is that you always have the ambient dimension, of course, as an upper bound. And we also have what we call the affinity dimension as an upper bound. And okay, so this is something which depends only on our matrices. Okay, so this notation for me is going to denote the matrices in the IFS. Okay, it's this tuple matrices. I won't actually define the affinity dimension precisely, I think, it's because it's not important, but it will come up later. So I thought it's worth mentioning. And also, so this upper bound holds regardless of overlaps, regardless of anything. Okay, so this is always true. And so as well, with the set of projections, there's also the question here, when is there actually equality here? So that's also like an important research area. And for measures, there's a similar result due to probably in the most generality to Eno Rossi, stating that if you take the upper packing dimension of the self-affine measure, okay, so it's not important again what the packing dimension of the measure is really today. So, but what's important is that this object also has a natural upper bound. And that natural upper bound is a similar formula where the ambient dimension appears. And there's a notion of a dimension analogous to, I guess, this affinity dimension just for measures. And this dimension, in this case, is called the Lyapunov dimension. And I'm going to denote it like this, dim L of this measure. Okay, that's something again which I won't define because it's not important, but it's good to know that there is this upper bound which always holds. Okay, so these things always, this holds for any choice of P as well. Okay, so this is actually even more general. So this is not only for Bernoulli measures, those are the measures we're going to be interested in today, but this is actually true for all ergodic measures. It's kind of upper bounds. Right. Okay. Any questions so far? Okay, so we've seen that there's a general Marstrand-Mattila projection theorem. There are sets of exceptional directions, and we're interested in what can we say when these are self-affine sets and measures. But this is still a bit too general in this sense. Okay, so we still need to zoom in a little bit more. And more specifically, what now I'm going to do now is to tell you guys what are the matrix tuples that we are going to consider. Okay, so that's going to be the next topic. So what kind of matrices are we going to be interested in? Okay, so first of all, we have the following kind of classification of the way that we can think about these matrices. So there are three cases which are important. There's something when we call a matrix tuple to be reducible. There's also one which we call irreducible and strongly irreducible. So what does irreducible mean? So for a matrix tuple, it's important that we are, so right, for a matrix tuple, what we are interested in really what is different products of the matrices. Okay? Because that's basically what determines where your point is going to land in this self-affine set. So we're interested in these kinds of products. And so we have a notation for this. Let this be SA. So this is the subsemi group generated by the tuple itself. Okay, so you take all possible finite products of the matrices. Okay? And it's really these products that we are giving different conditions on is what's is the important thing. So we're going to say that the matrix tuple is reducible if there exists a proper non-trivial linear subspace which is left invariant under the maps in the tuple. Subspace V such that AI times V is equal to V for all of the maps in the tuple. Okay. I'll give you an example in a minute, but let me just tell you about the other two categories first. So we say that a tuple is irreducible if it is not reducible. Okay, so that wasn't difficult. If not reducible. Okay, so you cannot find such a proper nonlinear subspace. And we're going to say that it is strongly irreducible if not only does a proper linear subspace like this does not exist, you cannot even find a finite union of them. Okay, so there does not exist finite union of proper non-trivial linear subspaces.
This is like irrational relations, right?
In the self-similar case, yes, you can think about that. Basically, yes. Such that AI leaves this set unchanged. Okay, so yes, that's an example, but let me give you perhaps even better examples on the plane. Okay, so there actually it's very easy to characterize all of these three sets. So on the plane, the reducible guys are exactly the matrices which you can take into a upper or simultaneously with the coordinate transformation into either all of them are upper triangular or all of them are lower triangular matrices. Another way of thinking about, or even simpler, right, is like a diagonal matrix is just going to leave invariant, let's say, the x-axis. Okay, so that's the example that you can think about there. What are the irreducible ones, which are neither in the other two? Well, those are exactly those tuples which contain at least one diagonal and at least one anti-diagonal matrix as well. Okay, so these are the kinds of guys which are living here, but in neither of the other two. And basically everybody else is here. Okay, right, so this anti-diagonal and diagonal one is not reducible.
So if you assume also that one of the guys is proximal, then yes. Otherwise, you can have rational rotation.
Yes. Yeah. So this is outside of the self-similar world.
Yes.
Yeah.
Yes. So in the actual self-affine world, these are the three cases and not more. But if you add the self-similar world, then you have this simple rational rotation.
Yes. Yeah, because rational rotations would come here as well. Yes, exactly, and exactly what Balázs mentioned, this proximality is also an important thing. So before I say what that is, let me just emphasize that today this is the only subset of matrix tuples that we're going to be interested in. Okay, this is the one that we are going to concentrate on. And so, assuming that we are within this class, okay, so what does proximal mean? So I'm just going to write it here now, but this is to be thought of from now on as a given assumption. So assuming strong irreducibility. What does it mean for a tuple to be proximal? Well, it's exactly what Balázs already hinted, is that so you can find a matrix in your subsemigroup, so a product of your matrices for which it has a simple dominant eigenvalue. Okay, so which really separates away from all the other ones. So there's a matrix in your subsemigroup with simple dominant eigenvalue.
What do you mean simple dominant eigenvalue?
So remember also that we are strictly contracting matrices. So everything is just eigenvalues between 0 and 1. Simple, I mean that it's real, and it has a so with multiplicity 1 is the eigenvalue. So again, this is ruling basically out self-similar kind of behavior.
Is it the largest?
Yeah, yes, that's basically what I mean by dominant, that it's the largest.
The single largest.
Yes. Yes. This is important because this is really determining how the balls are kind of shrinking.
Is it so can there be non-real ones which have higher modulus?
No.
So this is really the largest absolute value, and this is real, and this is real.
Yes.
Okay.
Yes.
So in some sense, it's also an assumption. On the plane, it's not an assumption. They are self-similar.
Yes, or this is automatic, right?
Yes. But in higher dimensions, that plane that you have a dominant eigenvalue and not like the behavior described is somewhat a mild assumption.
Yes. Yeah, so we will see that these kind of matrix tuples, in a topological sense, they are big. Within the set of tuples, this is going to be an open and dense set. That's basically why we are restricting our attention to these kinds of guys, because there are so many of them. Okay. Right. So that was proximal. Now, unfortunately, there are horrible many different types of other notions that I also need to say, or should say at least in some sense. But 30 minutes have gone already. That's not so good. All right. So I will maybe not go into all of the details here into each of these. Okay, so sort of generalizing this proximal idea or strengthening it, or making a stronger assumption is what's called pinching. So for a matrix to be pinching, not only do we want it to have a simple dominant eigenvalue, but you want it to be diagonalizable and have all of its eigenvalues distinct in absolute value. Okay, so basically everything is real and everything has a different modulus. Okay, so that's a pinching matrix, and a pinching tuple is if you can find a matrix within the subsemi group which is pinching. So there is a product of the matrices where every eigenvalue is going to be different. Okay, right? And clearly, if you assume pinching and you're in this irreducible case, then you're automatically proximal, right? Because there you only need the dominant, the largest one to be different. Okay, so this is something stronger. Now, well, on the plane, this is where the story would end. Unfortunately, we have to go into higher dimensions. So unfortunately, these notions have higher dimensional analogs as well. And this is where things get a little bit messy, because we have to, or I need to, introduce the exterior products. So I will be pretty brief with these as well, but let me just write a few things down at least. Okay, so we pick a k from 1 to d minus 1. And the kth exterior product of RD. So it's denoted like this. So the wedge product K RD. How do you want to think about this? I'm going to try to simplify it as much as I can. So this is a D choose K dimensional vector space. And what's important for us is that we can define linear maps on these based on a matrix coming from RD. Okay, so given a matrix, a D by D matrix, which is invertible, we can define a linear map. This a wedge K like this. And what this is this is basically a matrix on this larger dimensional space. Okay, so this is a matrix. This is how we want to think about it. With this many dimensions, D choose K. And what's important about this map is that if you take the singular values of this matrix, so you take the singular values of this matrix, well, that's nothing else than products of the singular values of the original matrix. Okay, so we have this A, it has singular values, alpha 1, alpha d, right? Which basically tells you how it distorts a unit ball into an ellipse. And then the singular values of this wedge version is simply k-fold products of these. Okay, so it's simply of the form alpha I1 times alpha ik, where these indices, we just assume that they are ordered. Yes, so every sorry, this is a
They are different, right? They are different, right?
The singular
singular values, they don't necessarily have to be.
Oh yeah, but the indices are.
The indices, yes, they are strictly different. Yes. Ik less than or equal to D. Yes. So in particular, the matrix norm of this guy is equal to the product of the k largest singular values of the original. So this is somehow telling you how this thing is distorting parallelepipeds in higher dimensions like this. And so the reason why this was introduced is because now you can introduce, okay, so maybe I have to switch pages then, is that, so now you can say that a matrix tuple is strongly k irreducible. But remember, we have strongly irreducible. This is now saying strongly k irreducible means that the tuple, right, we just defined this tuple, which is just a collection of these matrices. We have defined already what strongly irreducibility means. So strongly k irreducible is going to mean that this tuple is strongly irreducible. Similarly, you can say that some guy is strongly k-pinching, right? In the same analogous way. And you can strengthen this even more by saying that something is strongly k-pinching if there's a matrix whose exterior products are simultaneously strongly pinching for every k. Okay, so, and I said this can be a bit much. Firsthand, if you want, you can just think about the plane, and there you don't even really need to think about these. Okay, because there, right, because k goes from 1 to d minus 1, so there's nothing happening. Okay, and then there's one final thing that I still need to put on the board. Oh, if this wasn't enough already, is that a matrix tuple is Zariski dense. So what does this mean? Okay, so I will write down the formal definition and then try to make a bit of sense of it. So you can kind of think about it that, no, let's write down the definition. So, this is kind of like an algebraic condition saying that your matrices So there's like no resonance or something between them in the following way. So if you take a polynomial P, which takes as input matrices, and it spits out a real number, then if it's true, if for every polynomial such again, so if the polynomial takes value 0 at all of the, for all of the finite words in our alphabet. So you take all finite words, you evaluate the polynomial at those matrices. This thing is 0. Well, then this has to imply that, in fact, this polynomial is 0 everywhere. So PA is 0 for all matrices. So it somehow wants to be like a generalization of linear subspaces, I suppose. So like in a linear subspace, or you can also think about this polynomial. Let's say that the polynomial is equal to the determinant of the matrix. Let's say, right? That's a polynomial in terms of the entries of the matrices. And you could say that, okay, so right, and if you take polynomials which are determinant +1 or -1, those are an actual linear subgroup of these matrices. So in particular, those matrices are in this sense not Zariski dense. Okay? So this is somehow saying that algebraically, these set of matrices is basically as large as possible. Okay, so there are really no kinds of resonances going on here. That's the best intuition that I can give you at the moment. Maybe Balázs has something better than this.
Not really.
Yes. But the thing is that what turns out is that this works, this condition. So why do I say that this condition works? Okay, so maybe I should just mention in words that how is this Zariski dense connected to the previous conditions. So Zariski dense, it always implies these two conditions. So the strongly K-reducibility and the strongly pinching thing. So, and in dimension 2, it's actually equivalent. So again, in dimension 2, life is easy. You can forget about this, basically forget about this, and just think about strongly reducible proximal matrices. But in higher dimensions, life is tough. But the other way, so if you assume these two conditions only, then that does not imply Zariski denseness in dimensions 3 and above. So this is strictly a stronger condition. So after boring you to death, yes. Say that again.
So there are examples. Of
yes, which are not in these categories. Yes, yes. I don't have it written up, but there's one in our soon to be released preprint. Yes. So it is genuinely a stronger condition. So after having bored you guys to death with these things, let me say that the Zariski denseness, as I mentioned, this is really topologically a dense set. Okay, so this is open and dense within the tuples of matrices. And so what is the main theorem? Well, perhaps after all of this suffering, you guys can guess. So this is our main theorem concerning the set itself. Is that
just one more point?
Yes.
Regarding the Zariski density also is an open and dense set of cycles. So
or fixed size.
Yes, yes, for fixed size, yes. wanted to mention that as well. So if we take a self-affine set, in RD, whose matrix tuple is Zariski dense, so the associated tuple is Zariski dense. Notice that this assumption is only on the matrix tuple itself. It says nothing about the geometry of the set itself. So only assuming these, then our exceptional set is actually empty. Okay, so the Hausdorff dimension of the projection is equal to the, we can actually say something a bit stronger. So not only can we say it with the Hausdorff dimension, but we can say it with the upper Minkowski dimension of the set. So this is true for every, and this is really important part, for every direction. Okay, so there's no separation condition on the set itself, which is an important thing. We are in arbitrary d dimensions, and all we're assuming is a condition on the tuple itself, which, as Balázs mentioned, is an open and dense subset of all the tuples. And just based on these assumptions, we are able to say that the set of exceptional directions is actually empty. Okay.
Does this make sense for the such similar case?
I don't know actually what the best we know in the similar.
There is the Hochmann-Schmerk, but I think it's
Yeah, but there are some extra conditions.
Yes, what you need is that basically also a condition on the linear parts, which I think says that the generated semigroup is dense in the simple orthogonal group.
And so my question is that if the special case when similar, so then what is the Zariski denseness? Is it a stronger or weaker condition than the
So I think,
or does it make sense?
so no, because the orthogonal guys are not Zariski dense in the set of matrices. Right? But if you restrict yourself inside orthogonal group or the simple orthogonal group, then I just bet now, and I don't know that, but I would guess that this density assumption would mean Zariski dense. So one, or in that special subgroup, basically the density should mean the Zariski dense be the same. But I'm not 100% sure.
So that's for your dimension and arc. Oh, so similar case.
Yes, but I think the assumption is not the Zariski dense. The assumption is that the induced subsemic group is dense.
Yes.
The simple. Yes. But I would bet that this can be at that situation reformalized for Zariski density. I don't know.
Yes. Yes. So I should just mention what was the closest that we got in the self-affine case until now? Probably the best is due to Hochmann-Rappaport, who on the plane were able to get this with the extra assumption of exponential separation conditions. So there you actually need separation on the set itself. Okay, so that's basically what we are getting rid of and going into higher dimensions simultaneously. Okay, so that's the closest in this direction. But if you also look at very recent preprints of Feng, Shi, or Morrison Sert, there you can actually see that this living in this irreducible world is actually in some sense necessary, because once you go out of it into the reducible world, then there again you can start constructing weird examples where the set of exceptions becomes very large. So this is sort of, we're not claiming that the Zariski density is the optimal condition here. But in this direction, this is certainly something which goes well beyond the current state of the art at the moment. So this is the main result. I should also say that there's a similar version of this with the measure version of this, only for Bernoulli measures. I'm not going to write that up. Instead, I'm going to write up a very simple little corollary of this, which is also important because it also sheds light on a very important folklore open question in the area, and that's about the existence of the Minkowski dimension of sets. So a direct corollary of this is that if we have the assumptions as in the theorem, plus we assume that the upper Minkowski dimension of the set is at most 1 to begin with, then that implies that its Minkowski dimension exists and is equal to the Hausdorff dimension. We do not know whether or what the actual relationship of it is with regard to the affinity dimension that I mentioned earlier. So that's open, but this string of equalities we can actually have. Right?
So
and this was
what is that you don't know?
Is whether this number is also equal to the affinity dimension. Yes. Okay. So, right, and this is an open folklore question, which most of people think is true, that the Minkowski dimension of a self-affine set should exist. And this is confirming it under these assumptions, with this extra assumption that the upper Minkowski dimension to begin with was at most 1. Why is this true? And this is what I will finish with. You can just, this is a one-line proof after all of this. Right? So let's start from the left-hand side here. The lower Minkowski dimension is always bounded from below by the Hausdorff dimension of the set. The Hausdorff dimension of the set is always bigger than its projection, or at least as much. Then Hausdorff of the projection. From the theorem, we know that that can always be bounded from below by this number, regardless of which direction you. This is why it's important that we have this theorem for every direction. So this is at least this minimum. And we assumed that the upper Minkowski dimension was at most 1. So the minimum is attained by that. And we are done, right? Because the upper Minkowski dimension is also an upper bound for the lower Minkowski dimension. Right, and I'll finish there.
Thank you very much. Questions, comments?
I have a very simple question. How hard is stuff? So how long is your paper?
It's getting longer and longer.
Yeah, and now we are 40, 50 something.
I think 50 plus.
Yes. And although one of the main things we are relying on is Ariel's 3-dimensional result, and we use that was a black box, and still.
Yes.
Yeah.
Yes, and yeah, I didn't say anything about the proof of this, but I mentioned that there's a measure result as well, and that also uses some heavy lifting from Hochman-Schmeck and local entropy averages.
Do you prove directly that measure result in this corollary?
Yes, so the measure part is, so the measure theorem is a very important ingredient in the proof of this, in the set one.
It's not direct.
Not entirely, because so I didn't write it on the board, but the measure one we can only prove for conditions which are not Okay, so there we need the exponential separation.
Oh, I see. Yes.
So the extra step that you need for the proof of is to be able to construct subsystems of the original self-affine set, right? Because here we don't have any type of separation condition. We need to construct subsets which have the desired separation to be able to apply the measure result. And actually that part is kind of non-trivial as well. And in the self-affine world, it seems to be kind of novel too. So that method as well could be useful.
The difficulty if the weaker condition is irreducible, not stronger.
Many, I think. So then lots of behaviors, and I think the first number
The
measure
first number measures beginning point. I
has a completely different kind of case. And also, yeah, relies on that. The Hook-Markov method relies on that. That in this case, the first number measure has very specific, very good properties, which are not true anymore for the use. For the use.
Yeah, so that this went so easily, so it's natural to ask what if that one is replaced by some larger number. Is there any hope, especially to get this corollary? I suppose you don't want to limit yourself to one.
Yes, I mean that would be nice, but
Really hopeless?
yeah. So we are genuinely using the fact that we are projecting just onto lines in more than one way. One of the ways that we are doing it, or where we are doing it, is actually when we're constructing our subsystem. We need that to satisfy a certain domination condition. And so the nice thing about when you assume that you're in the world of dimension at most one is that the singular value function of the matrix, which you know appears in the definition of the affinity dimension. So the value of the singular value function for the matrix is equal to the matrix norm. And that is no longer true once you go beyond dimension one, and things fall apart very quickly from there. So in other words, we can, because of this property, we can approximate the affinity dimension very well just by using cylinder sets. And once you go higher in dimension, then that's no longer true. And yeah. So there are genuine difficulties in going beyond.